ESS Atmospheric Systems and Pollution Management Part 2 will focus on the greenhouse effect, a natural and critical phenomenon that maintains the Earth's temperature at a level suitable for life. The greenhouse effect is not synonymous with climate change. Be thoughtful here. The significant ideas are the atmosphere is a dynamic system that is essential to life on Earth. The behavior, structure, and composition of the atmosphere influence variations in all ecosystems. Here is the outline of all the available movies in this unit called Atmospheric Systems and Pollution Management. Use this outline to find the movie you need for review. This movie is focused here. The atmosphere is an extremely thin layer of gases that surrounds the Earth's surface, held close to the Earth by gravity. The layer is so thin that if you could drive through it from the Earth's surface to the top edge of the atmosphere, you could do so in less than an hour without breaking the speed limit. The mixture of gases known as our atmosphere is a dynamic system with storages and flows, inputs and outputs, and the atmosphere is critical to life on Earth. The atmosphere is a mixture of gases, and now's the time to take some notes. The air is a mixture of nitrogen, N2, oxygen, O2, with smaller amounts of carbon dioxide, ozone, argon, water vapor, and other trace gases. Here is the relevant IB syllabus statement. It is the same statement that I just read on the last slide. I do want to make a point, though, that water vapor, seen here, is gaseous water. It's invisible to the eye. Liquid water in the atmosphere is visible to the eye, such as clouds. This is an important slide to study. The atmosphere is almost entirely nitrogen, N2, and oxygen, O2. Keep this in mind. Water vapor, carbon dioxide, and ozone represent just fractions of a percent of the entire gaseous mixture. The atmosphere is predominantly a mixture of nitrogen and oxygen with smaller amounts of carbon dioxide, ozone, argon, water vapor, and other trace gases. Solar energy is a critical energy input to the atmospheric system. Solar energy serves to stimulate photosynthesis. It serves to warm the Earth. It unequally heats the Earth, which drives air movement, winds. It evaporates water, and so drives the water cycle. So here are the IB syllabus statements that drive this movie forward. Describe and explain the greenhouse effect. The greenhouse effect of the atmosphere is a natural and necessary phenomenon maintaining suitable temperatures for living systems. Before diving into an explanation of the greenhouse effect, I just want to emphasize a point in the IB syllabus statement that I just read to you. With the greenhouse effect, the Earth's average temperature is a comfortable 15 degrees C. Without the greenhouse effect, the Earth's average temperature would be negative 15 degrees C. The two principal greenhouse gases responsible for the natural and critical phenomenon known as the greenhouse effect are water vapor and carbon dioxide. Take note. But there are other greenhouse gases, and human activities are increasing greenhouse gases. Those gases, other than carbon dioxide and water, are methane, dinitrogen oxide, otherwise known as nitrous oxide, chlorofluorocarbons, CFCs, and tropospheric ozone. It's important to note that the increase of greenhouse gases due to human activities is what we explore in the next unit on climate change. Climate change is the next unit. Also remember that the greenhouse effect, the subject of this movie, is not synonymous with climate change. The greenhouse effect is a natural and necessary phenomenon important to life on Earth. Okay, let's dig into an explanation of the greenhouse effect. Over the next 10 slides, I want to build a foundation that is crucial to understanding the greenhouse effect, and it starts with a look at wavelengths and the interaction of atmospheric gases and wavelengths of energy. The electromagnetic spectrum has short, high-energy wavelengths and long, low-energy wavelengths. The wavelengths that you should be familiar with are those of the visible spectrum. These wavelengths are used by animals for sight and by plants for photosynthesis. The visible spectrum wavelengths are between 400 nanometers and 700 nanometers, or 0.4 micrometers to 0.7 micrometers. Other wavelengths important to our discussion and moving forward will be UV wavelengths, shorter and higher energy than the visible, and infrared wavelengths, which are longer and lower energy than the visible wavelengths. Infrared wavelengths are also known as heat. Again, here's the electromagnetic spectrum. Short, high-energy wavelengths at this end of the spectrum and long, low-energy wavelengths at this end of the spectrum. Here is the visible range, expanded 400 nanometers to 700 nanometers. Here is the UV range, shorter wavelengths than the visible with higher energy. And here is the infrared, longer wavelengths and lower energy than the visible. Here are the wavelengths that stream toward the Earth from the Sun, arriving to the outer edge of the Earth's atmosphere in about 8 minutes from 150 million kilometers away. The units here are micrometers rather than nanometers, but that doesn't really matter. The UV wavelengths are between 0.2 and 0.4 micrometers. The visible wavelengths are between 0.4 and 0.7 micrometers, and the infrared wavelengths are longer than 0.7 micrometers. Here are the electromagnetic wavelengths that emanate from the Sun toward the Earth. We can see here this line provides a frequency of wavelengths that enter the Earth's atmosphere. We can see low frequency, a very high energy short wavelength, a high frequency in this range of wavelength, and a low frequency here, longer wavelengths. But this is the radiation entering the Earth's atmosphere. Now this curve here is the radiation that reaches the Earth's surface. Notice that there's been a change through here. In fact, of all the wavelengths arriving to the Earth from the Sun, as seen here, many of the short wavelengths do not reach the Earth's surface. You see, they're not reaching the Earth's surface here, and they're removed by the gases of the atmosphere. Notice that change. Here are the wavelengths entering the atmosphere, but here are the wavelengths. Here are the wavelengths reaching the Earth's surface. Now the UV wavelengths, these short high-energy wavelengths, are removed by gases in the atmosphere, particularly ozone gas. Remember this when we study stratospheric ozone depletion. Of all the wavelengths arriving to the Earth from the Sun, as seen here, it's mostly visible wavelengths that get through to reach the Earth's surface. Of all the wavelengths arriving to the Earth from the Sun, as seen here, some are reflected by surfaces with high albedo, snow, ice, and the tops of clouds. UV wavelengths are absorbed by gases in the atmosphere, ozone particularly, and about 50% of all the wavelengths arriving from the Sun reach the surface of the Earth. These are the short wavelengths in the visible range. And not to digress, but it is important to remember that the Earth radiates long wavelengths, heat, back to the universe. And the total energy absorbed by the Earth as short wavelengths can be seen in this curve, and that total energy in the short wavelengths that arrive to the surface of the Earth is equal to the total energy re-radiated to the universe as long wavelengths as seen in this curve. It's an equal in, equal out with an equilibrium in the Earth's average temperature. But human activities are changing this equilibrium. So I've returned to this IB syllabus statement, knowing that I have not really addressed this statement directly yet. What I need to do is describe and explain the greenhouse effect as a natural and necessary phenomenon, maintaining suitable temperatures for living systems. The greenhouse effect of the Earth can be understood in the image of a greenhouse. Inside the greenhouse is the Earth's surface, but the glass represents the gases of the atmosphere. Short, visible wavelengths stream through the atmosphere, represented by the glass of the greenhouse. The Earth absorbs the short, high-energy wavelengths and re-radiates them back out as long, low-energy wavelengths, heat. The gases of the atmosphere, represented by the glass here, absorb the long wavelengths and re-radiate those long wavelengths back to the Earth, serving to warm the Earth. One more time, the greenhouse gases, water vapor, carbon dioxide, and others, absorb the long wavelengths radiated by the Earth. It absorbs these wavelengths and then re-radiates them back to the Earth, keeping the Earth warm, a natural effect. Solar energy streams towards the Earth. The high energy wavelengths are removed before they reach the Earth, when they are absorbed by the atmosphere before reaching the Earth's surface. This includes UV radiation, which is absorbed in the stratosphere by ozone. The short visible wavelengths reach the Earth's surface and are re-radiated as long wavelengths as heat back out, but the atmosphere absorbs the infrared heat and re-radiates it back to the Earth, serving to warm the Earth. Some heat is radiated to the universe. This is a nice graph that displays absorption of energy by wavelength of various gases: methane, nitrous oxide, oxygen and ozone, carbon dioxide, and water. We have short wavelengths here, long wavelengths here, and these peaks indicate high absorbance. For example, notice that methane absorbs long infrared wavelengths. Nitrous oxide absorbs long infrared wavelengths. Oxygen gas and ozone absorb very short wavelengths. Carbon dioxide and water both absorb long infrared wavelengths. Now, there are two things to notice. No gases absorb the visible wavelength range. Visible wavelengths get all the way through to the Earth's surface. Carbon dioxide, water, nitrous oxide, and methane are all greenhouse gases that absorb long infrared wavelengths radiated from the Earth's surface. These gases re-radiate heat back to the Earth. Short, visible wavelengths reach the Earth's surface. The Earth radiates long infrared wavelengths, heat back out. Gases from the atmosphere absorb those long wavelengths and re-radiate them back to the Earth to warm the Earth. The greenhouse effect is natural and important for providing a suitable temperature for life on Earth. The greenhouse gases are water vapor, carbon dioxide, and others. Once again, solar energy streams toward the Earth from the sun. Surfaces with high albedo reflect the solar energy back out, but short, visible wavelengths reach the Earth's surface. The Earth radiates long infrared wavelengths, heat back out. Gases from the atmosphere absorb those long wavelengths and then re-radiate them back to the Earth to warm the Earth. Solar energy streams toward the Earth from the sun. Short, visible wavelengths reach the Earth's surface. The Earth radiates long infrared wavelengths, heat back out. Gases from the atmosphere absorb those long wavelengths and re-radiate them back to the Earth to warm the Earth. This is the greenhouse effect. One more time, and the last time, short wavelengths pass through the gases of the atmosphere to reach the Earth's surface. The Earth radiates long wavelengths, heat back out, but gases of the atmosphere absorb those long wavelengths and re-radiate them back to the Earth, warming the Earth. This is the greenhouse effect. At this point, you should be able to describe and explain the greenhouse effect as a natural phenomenon that regulates the temperature of the Earth. Without greenhouse gases, the average temperature of the Earth would be a cold -15 degrees C. With greenhouse gases, the Earth is a comfortable positive 15 degrees C. As we wind this movie down, I'd like to remind you of a couple of relevant IB syllabus statements that I've presented previously. Discuss the role of the albedo effect from clouds in regulating the global average temperature. Secondly, clouds form in the troposphere. Albedo is defined as the proportion of the incident light or radiation that is reflected by a surface. It's measured on a 0 to 1 scale. Surfaces like snow, ice, or the tops of clouds have a high albedo, approaching 1, serving to reflect light away from the Earth, thus reducing the amount of solar energy absorbed by the Earth's surface. Snow, ice, and clouds with their high albedo serve to cool the Earth. Clouds form in the troposphere, and their white tops with high albedo reflect solar energy, keeping the Earth cooler. The discussion around clouds and their albedo and the regulation of the Earth's temperature will come when we study climate change, because as the Earth warms, one might predict more water vapor in the atmosphere due to evaporation. With more water in the atmosphere, more clouds might form, and more clouds would serve to reduce temperatures, not increase them. This is because of the high albedo, the reflection of light. This would be a negative feedback process worthy of discussion. Surfaces with high albedo, such as snow, ice, and cloud tops, reflect light. More snow, ice, and cloud would serve to cool the Earth. But if ice melts, exposing blue water, water absorbs solar energy. This would warm the water, causing more melt, causing more solar absorption, causing more melt, a positive feedback loop. At this point, you should be able to discuss the role of the albedo effect from clouds in regulating the global average temperature. More on this topic in the unit on climate change. And from part 1, I've already mentioned that living organisms have transformed Earth's atmospheric composition and vice versa throughout history. How so? Well, photosynthetic organisms release oxygen to the atmosphere, photosynthetic organisms take up carbon dioxide from the atmosphere, and humans have released carbon dioxide and other gases into the atmosphere. Water and carbon dioxide are not the only greenhouse gases. Greenhouse gases include methane, nitrous oxide, CFCs, and tropospheric ozone formed as a part of smog. All of these gases arise due to human activities. Hopefully you can see the impact of human societies on the atmosphere. Take some notes. Name 5 greenhouse gases. Changes in the greenhouse gas concentration in the atmosphere over the last 100 years, as you can see in these slides, has resulted in what's called an enhanced greenhouse effect, resulting in a rise in the Earth's average temperature. Have you taken some notes? Name 5 greenhouse gases. This table shows the change in the concentration in various greenhouse gases since the start of the Industrial Revolution moving forward. You can see changes in all of these greenhouse gases. Human activities have increased the concentration of greenhouse gases. Can you name 5 greenhouse gases? But don't forget that the greenhouse effect is a natural phenomenon important to the suitable temperatures on Earth for living things. The combustion of fossil fuels and deforestation have resulted in a dramatic increase in the concentration of carbon dioxide in the atmosphere over the last 100 years. Now, as I talk about carbon dioxide here, don't forget that water vapor is also an important greenhouse gas. But the atmosphere is a dynamic system with inputs, outputs, flows, and storages, and the atmosphere has undergone changes throughout geological time. As I mentioned just a few slides back, the atmosphere of the Earth had no oxygen until the evolution of photosynthesis resulted in oxygen's release to the atmosphere. But the concentration of carbon dioxide in the atmosphere has also varied dramatically over geological time. And that brings us to the end of Atmospheric Systems and Pollution Management, Part 2.